In this example, I'd like to look at a simple example where we set up the virtual work equations, but we're going to use variations or test functions that are non-admissible, so the ones that do not satisfy the kinematic boundary conditions, or not zero where the kinematic boundary conditions are known. So basic problem is a bar here with a distributed load B of x and an end force P. It's built in on the left end. And the space of solutions, S, is given to us by functions u of x such that u is equal to 0 at 0. And the space of test functions, the standard one, is ones where we respect the kinematic boundary conditions by requiring the test functions to also be 0 anywhere we know the kinematic information. Okay, so, but we don't always have to do this. We could set up an alternate space of test functions v such that there are no restrictions on the test function. So we don't respect the kinematic boundary conditions. So in this case, if we were to look at our system and consider a virtual motion of it, so let me just redraw it here. I'll quickly sketch it in. Maybe we leave the force out for a second here. If we consider a admissible variation that doesn't respect the boundary conditions, it's possible that we can be considering a motion where there's a finite amount of displacement of the bar at x equals 0. So in this case here, there's going to be a contribution to the external virtual work from the support reaction, which I'll call R0. So we still have our force P, and we still have B of x acting on the rod. So if I go to write down the expression of external virtual work equals internal virtual work, in my external virtual work expression, I'm going to need to account for this support reaction. So let's go ahead. We have three contributions now to the external virtual work. So from the support reaction, I'm going to get a minus R0 del U evaluated at 0 plus the force P times del U at L, so external virtual work at the applied force. And then there is the distributed load, B of x, so I'll get an integral 0 to L, B of x del U of x dx, and this is all equal to the internal virtual work, which is the integral 0 to L. Oops. Got ahead of myself there. 0 to L R of x del epsilon of x dx, where del epsilon is just defined to be the derivative of del u with respect to x. So this is my new virtual work equation here, and we've picked up this extra term here from the support reaction because del u of 0 is not equal to 0. If del u of 0 is equal to 0, then that term minus R0 would disappear. And the reason for the negative sign is because the way I've drawn my picture over here, I've put my support reaction pointing to the left, and the motion is assumed positive to the right, so they're going in opposite directions. And so we pick up a minus sign.